In this video, we'll continue to look at CSEC Physics past paper questions. Now, in this particular question, we will look at magnetism, electromagnetism, the DC motor, and this question comes from January 2012, paper 2, question 4. So, to look at the question, part A of the question says, figure 3 shows a diagram of a single DC motor. So, this will be figure 3, shows a diagram of a single DC motor connected in a circuit. And it says, with reference to the DC motor shown in figure 3, explain how the coil is able to rotate, right? And that question is worth 6 marks. So before we proceed to doing that, let's identify the parts of this DC motor. All right, so this is a DC motor. Of course, we have the magnets. So this is the north pole and the south pole of the magnet. And of course, by now we should know that the magnetic field runs from north to south pole. And of course, this is expected to be a uniform magnetic field. This of course is a coil which is going to basically rotate within the magnetic field. And here we have an external circuit. Now the external circuit comprises of course a cell, there's a variable resistor, and of course there's a switch which is shown to be closed, and there's a current flowing in the external circuit. Now the current is able to flow through the coil via so these are the carbon brushes. These rectangular looking things are the carbon brushes, right? And of course, if you're watching this video, then of course I would recommend that you look at the question so you could get a better idea, or at least a nicer drawing, right? So yes, so the circuit is closed and there's a current flowing from the positive terminal of the battery. This is positive, that's the negative, and it's flowing through this carbon brush. Let's call this carbon brush X. So let's call this carbon brush X and call this one Y, right? Now let's also label the sides of let's label the coil. Let's call this A, B, C, D, right? Good. So this external circuit is driving a current, and the current I flows through carbon brush X. And here we have the split ring commutator. So this is a split ring commutator, and the ends of the coil go through the space, and of course they're connected or touching in contact with the split ring commutator. And of course through that connection, the current is actually going to be able to flow through the coil, around the coil in the direction A, B, C, D, and then exit and flow back to the external circuit through carbon brush Y, right? Now, how is this coil able to turn? Now we know from magnetism and magnet effects that whenever there's a current carrying conductor placed within a magnetic field, the field which is present within the conductor due to the current flowing and the magnetic field in which the conductor is placed, these fields will interact, and as a result a force will be exerted, right? A force will be exerted, for instance, on one side of the coil, and an equal force of equal magnitude which acts in the opposite direction exerted on the opposite side of the coil, and these equal and opposite forces produce what is called a couple, and of course the torque of this couple will cause the coil to rotate, right? So to analyze this even better, we'll need to apply Fleming's left-hand rule. Now according to Fleming's left-hand rule, if you hold the first finger and the second finger of your left hand at right angles, so that they point in the direction of the applied magnetic field and the conventional current respectively, then the direction in which the thumb points will give us the direction of the thrust or the force on the conductor. So we're going to be using Fleming's left-hand rule to predict the direction of the force on side AB and side CD of the coil. So let's apply it to side AB. Now, once again, if you're looking at the paper, the diagram is better drawn, and you can almost visualize that essentially the coil is essentially being pushed into the paper. So if we think of the magnet essentially as resting on the surface of the paper, we can think of the coil as essentially almost like being pushed into the surface of the paper, into the plane of the paper, right? And that will help when it comes to placing our fingers to align especially the second finger with the current direction. Right? So once again, the first finger points in the direction of the applied magnetic field. The second finger points in the direction of conventional current. And once again, when we speak about conventional current, we're talking about the direction that positive charge would flow. So if you notice from the battery or from the circuit, we have the current I flowing from the positive terminal around the circuit in this direction and not from the negative, which of course where the electrons would be flowing, right? So dealing with conventional current direction. So let's apply Fleming's left-hand rule. So this is a north pole, this is a south pole, and therefore the magnetic field points from north to south. So set our first finger so that it's basically pointing north to south. Now we need to rotate the hand so that the second finger points in the direction of the conventional current. So we go like this and something like that. And what this is basically showing is that this thumb is pointing downwards, and therefore what this means is that there's a downward force on side AB of the coil, right? So due to Fleming's left-hand rule, there is a downward force, let's call that force F, on side AB of the coil. Good. Now let's apply the same over onto side CD. So once again, the magnetic field is going from north to south. This time the current, of course, if this current is say going into the board, then of course this one is essentially coming out of the board. And so if we set our finger like this or like this basically, then this is going to show that there's an upward force on side CD of the coil. Right, so that's upward force F. So these forces are of equal magnitude but act in opposite direction. And of course, the lines of action are, there would normally be a perpendicular distance d between them, which of course would be equivalent to the width of the coil. Now, as mentioned in a previous video, these equal and opposite forces acting in this direction create or produce what are called a couple. They are a couple. Equal and opposite forces acting like this form a couple, and the effect of the couple is to produce a torque or turning effect. So essentially, this force will essentially cause the coil to in this direction, and this force this direction. And so basically what we have is, due to these two forces of equal magnitude and opposite direction on sides AB and CD of the coil, then these basically cause the coil to rotate. So essentially, that is how the coil is able to rotate, due to the force created by the interaction of the magnetic fields produced by the magnets and the current flowing and the current flowing in the conductor, right? Even though the question didn't ask for it, basically we can see that there's a space between the split ring commutators. Now essentially, when say the diagram is not so clear, but of course once again if you look at the diagram in the question, you will basically see the space clearer, right, more clearly. So essentially, when the coil has rotated say through 90 degrees, then the ends of the coil will be perfectly aligned with the spaces, which means that the coil will no longer be connected to the external circuit. There will be no current flowing in the coil, and because there is no current flowing in the coil, there can be no force on the sides of the coil. Now, what does this mean? Does this mean that the coil will come to a stop? No, the coil doesn't stop, because the momentum of the coil will keep it moving or keep it rotating until these ends once again come into contact with the split ring commutators, and once again the current starts to flow. Now, after about a 180-degree turn or half a revolution, essentially these sides are interchanged. So if we label this side AB and this side CD, then essentially CD is over here and AB is over here. But even though those sides that we labeled are interchanged, the current still flows in the same direction around the coil, and it therefore means that the forces are acting in the same direction on this side and on that side, and that basically causes the coil to continuously rotate in the same direction. Right? So that is basically how the coil is able to rotate, and of course continue rotating in the same direction. So that was part A of the question. Now part B of the question basically shows us a waveform. So according to part B of the question, the waveform shown in figure 4 here depicts the current through a resistor connected in an AC circuit. So this is referred to as circuit, an AC circuit, right? 1. Calculate the period and frequency of the alternating supply. So essentially what we have here is a wave. So we have a graph of current in amperes against time in milliseconds. So we need to pay attention to our units. So the current is in current is in amperes and the time is in milliseconds. And we want to determine the period and frequency of the alternating supply. By definition, the period is the time taken to complete one cycle. So one cycle, of course, would be from here. Let's call this point O. So this is the one cycle. From here to here, that's one cycle. And from here to here, that's another cycle. So the entire graph basically shows two cycles. So the period is the time taken to complete one cycle. And therefore, the period T would be equal to 30 milliseconds. But of course, we want to express that in seconds. So milli divided by 1,000 or multiplied by 0.001 or 10 to the minus 3. So this, of course, is equivalent to 0.03 seconds. So the period of this waveform of the alternating supply is 0.03 seconds. The next part of the question asks us to find the frequency. The relationship between frequency and period. So frequency F is related to the period T by the equation F equals 1 over T. And so this gives us 1 over 0.03, which of course is the same thing as 100 divided by 3, right? So that's 100 divided by 3, and that would be hertz. Of course, if you want to express it as a decimal to say 3 significant figures, then this is 33.3 hertz, right? So we managed to find the period as well as the frequency. So that's parts 1 and 2 of the question, of part B rather, parts 1 and 2 of part B. Part 3 says we're supposed to calculate the maximum power dissipated in the resistor, right? So we're given a graph of current against time. Now, what is the formula for calculating power? Right, so we use a formula P equals I squared R. The question asks us to calculate the maximum power. So the resistor, the value of the resistor is 45 ohms. So R is equal to 45 ohms. Now the current I is a sinusoidal waveform, but we're asked to find the maximum power, and therefore to calculate the maximum power, we would need the maximum current, which of course we can see from the graph is going to be 4 amperes. So we call that I max is equal to 4 amperes. And therefore the maximum power, P max, is equal to I max squared times R, right? And this gives us 4 squared times 45. So that's 4 times 45. That's 180. 16 times 45. How am I doing? Yeah. 180 times 4, that will be 720. So therefore this gives us 720 watts, right? So 4, 16. Yes, 16 times 40, that's 640 plus 80, 720 watts. And so therefore the maximum power dissipated in the resistor is 720 watts. So this, once again, this question was from January 2012, paper 2, question 4, in which you're able to look at the DC motor as well as do a few calculations pertaining to the waveform of an alternating supply.